So good morning or afternoon or evening, depending on where you are joining us from in the world. Welcome to our series on mangroves, and thank you for joining us. If you have been following our series closely, you will recognize today's speaker, Dr. Ray Ward, who spoke 2 weeks ago. But for those of you who were not part of his lecture, I'm going to reintroduce him. And Ray Ward is a professor at Queen Mary University in London in the UK. And he's been researching the impacts of global change on coastal and marine ecosystems for the last 18 years. He leads a range of projects globally that focus on the impacts of climate change on coastal ecosystems, including drought, flooding, storms, and sea level rise, as well as working for more than a decade and a half on investigating the role of blue carbon for climate mitigation and the drivers of rates of sequestration and influences on carbon stocks in coastal and marine systems. He also researches the impacts of pollution on coastal ecosystem resilience and ecosystem service provision. And as I said, he's at Queen Mary University. He's currently a reader working in the Climate and Earth Surface Science group. So welcome back, Ray, and we look forward to your talk today.
Thanks a lot, Doug. So I will just share my screen and then I'll get on with my talk. Here we are. So hopefully everyone can see that. So Dr. Ray Ward, and I'm going to be talking to you about carbon accumulation, carbon sequestration, and sediment accretion rates, and kind of the impacts that has on blue carbon and how that can be used to mitigate climate change. So, as I mentioned in the last lecture, but sort of a bit of a recap for those who didn't see the last lecture. We've got basically mangroves across the whole of our tropics with an area coverage of 358.99 kilometers squared, as reported by the Global Mangrove Watch in 2023. There's a range of different values around this, but they do cover an enormous area across the whole of our tropical coastal areas. They can be found in pretty much every country in the tropics that has a coastline. So there's 124 countries, and greater than 40% of that global area of mangroves is just in these 4 countries, all of which I do work in, and that's Indonesia, which has about 19%, Brazil has about 9%, Nigeria about 7%, and Mexico has about 6%. Now, in this lecture, I've kind of focused down on Brazil because I realized that when I had all the countries in there, it was about 70 slides. So I kind of tried to cut it down, and I thought, I'll focus on Brazil because it's basically one of the least well reported on countries of all of those concerning kind of blue carbon. So the reason that they're really important from a blue carbon perspective is that they are one of the most productive ecosystems. In the last lecture, I talked a lot about the kind of productivity of mangrove ecosystems, and this one's going to be a little bit more focused on how we get that kind of productivity and how it actually goes through down into the soils, and how that kind of works from a blue carbon perspective. Now, the importance of mangroves is that they provide that broad range of provisioning, regulating, supporting, and cultural ecosystem services to human populations. And one of the biggest ones that's kind of been worked on recently is that ability to mitigate climate change by locking away large amounts of carbon in the ecosystem themselves. But that's highly under threat, and the way that they kind of function is under threat from aquaculture, deforestation, urban expansion, and climate change. And where you've got those threats and you've got that degradation, then obviously that important ecosystem service of climate mitigation through blue carbon is under threat. So if you've got conversion to aquaculture, or if you've got a degraded ecosystem from kind of pollution from aquaculture, then obviously that means that you've got losses of those extremely kind of carbon rich ecosystems. So rather than them being a carbon store, which is really important, they become a carbon source. So therefore, they're actually releasing carbon up into the atmosphere, exacerbating climate change. You've got deforestation. Obviously, you've got losses of the biomass, but in addition to that, you have kind of losses of the soils in the mangrove ecosystem itself. If you've got urban expansion, urban areas moving into mangroves, complete loss of the ecosystem and complete loss of the carbon that's stored there. Okay, so there's a wide range of factors that kind of impact that. Now, from a blue carbon perspective, we think about our carbon, and Lau kind of produced this fairly good figure in 2004, suggesting that we've got a large proportion of our carbon up in the atmospheric pool, and that's the one that we're kind of slowly filling up by burning fossil fuels, etc. That's about 760 petagrams. Then we got that massive oceanic pool, which is, depending on which study you look at, it's between about 38 and about 40,000 petagrams of carbon. So that's the one that's kind of a real good kind of sink of that carbon. And we've got our geological pools. They tend to be a little bit more stable. And that's about 5,000 petagrams. Then we've got our soil pool, which is about 2,500, so about half the geological pool. And that's obviously a really important store of carbon, particularly in kind of terrestrial ecosystems. Then we've got our biotic pool, which is what we that's anything that's kind of alive. It could be the trees, or it could be, the animals that are kind of moving around there. And that's 560 petagrams of carbon. Now, from a climate change mitigation perspective, there's been several studies that have looked at how much of that atmospheric carbon is actually taken up at sea. And one of them has kind of suggested about 55%, so a little bit over half of the atmospheric carbon is taken up at sea. So that's really, really important. So were that to stop or kind of be impacted, then that would mean that there would obviously be a greater amount of that carbon left up in the atmosphere. Okay, obviously exacerbating climate change. Now, of that 55% of atmospheric carbon that's taken up at sea, a massive proportion of that, so 50 to 71%, so either half to kind of to almost 3/4 of that is stored as vegetated blue carbon. So if you think about all of our kind of oceanic systems across the world, so you've got carbon locked away in those kind of deep sea sediments. But a large proportion of it is actually just at those fringing margins, and that's stored in those vegetated blue carbon ecosystems. And they themselves cover less than 0.5% of the seabed. So you've got an enormous proportion of carbon locked up in a very, very small area. And what that means is first off, it's really, really important to preserve and conserve those habitats. Because if you lose that very, very small area, and I've already talked about that the fact that they are in many cases degraded or at threat of loss, then you've lost a huge proportion of that important ecosystem service of carbon being stored in those kind of coastal marine ecosystems. Now, when we're thinking about kind of blue carbon, we're usually talking about things such as seagrasses, salt marshes, and mangroves. And to kind of give you an idea of what we mean by that kind of importance, you can see there seagrasses have a huge amount of carbon that's locked away in their soils. And remember, the soils are typically the most stable part of that kind of blue carbon pool. From the perspective of you get fairly kind of high turnover if it's in the biomass. Salt marshes even greater, and slightly more in the biomass themselves. But as you can see there, from a mangrove perspective, they far outweigh the carbon that's stored in the other ecosystems, including what we kind of typically think of as one of those really kind of carbon-rich habitats, and that's tropical forest. So what's locked up in the soils of mangroves is much greater, even in the estuarine mangroves, than in the entire kind of tropical forest per hectare, so per unit area. Okay, so that's really important to put it into a kind of context. Now, to get an idea of why they're so good at kind of locking away carbon, we can think about the fact that, first off, where do we actually get this carbon from then? I've already mentioned that they are very, very kind of carbon rich, highly productive systems. So they're readily able to lock away carbon through kind of photosynthesis, through primary productivity. So you've got that direct kind of taking out of from the atmospheric pool and kind of storing it in that oceanic soil biotic type pool in the ecosystem. But you've not just got that carbon that's coming from directly from the ecosystem itself. You've also got it coming from other adjacent ecosystems. And as mangroves are kind of stored, kind of located in the littoral between the terrestrial and marine ecosystems, you've also got linkages between other coastal ecosystems. So I've got a picture of a seagrass. Now there's in areas where you've got mangroves and seagrasses kind of co-occurring, typically the seagrasses at a slightly lower elevation than the mangroves themselves. Then you've got input of organic material from the seagrass ecosystem into the mangrove and vice versa. So you've got kind of movement between the two ecosystems. So you've got that kind of allochthonous carbon that's being dropped into the mangrove ecosystem. Then you've got other sources. So typically where you've got kind of high fluvial inputs, you've got organic material running off of terrestrial ecosystems. Some of that will be dissolved organic matter, some of it will be particular organic matter, and that will be carried down and usually is typically deposited in the nearshore littoral, particularly around kind of mangrove ecosystems. Then you've got, as anyone that's kind of been walking around mangroves, you usually find bits of kind of filamentous green algae dotted around. If you're looking in kind of semi-arid ecosystems, we've got kind of apicum or sabca or that kind of co-component of the mangrove ecosystem, you'll find a lot of this kind of filamentous green algae, which is highly productive, and also kind of other smaller marine algae, things like marine plankton. Okay, so they can be an important source in some areas that are actually from the marine environment or from the aquatic environment that can be deposited in the mangrove itself and contribute to those extremely high rates of carbon sequestration in the soils. In areas where you've got macroalgal beds, that one's a kelp, so less likely to be occurring or co-occurring with mangroves, but other kind of macroalgal beds, you've got some of that will be washed up, particularly during periods of high storm activity, and that can be deposited on the mangroves. Some of it's kind of consumed by detritivores, and that kind of can end up in the soil component of the mangrove ecosystem. Other bits are just kind of rot away and slowly kind of become buried by minerogenic components of the sediment, and then they can actually be locked away in the soils themselves. You've got other kind of sources of marine sources of organic materials. Some of it's calcareous, things like coralline red algae or mel or whatever you call it in your specific area, and they can be other important kind of carbonate sources of carbon in mangrove ecosystems. In many mangrove ecosystems, you've got adjacent kind of salt marsh or kind of those kind of other kind of wetland environment ecosystems, which are often very highly productive as well, and they can also be important sources of organic material to the mangrove soil carbon stocks. And then this is from a mangrove kind of várzea area in north of Brazil. and you can have, obviously, you've got that extremely high in situ productivity, but also where you've got adjacent kind of really highly productive aquatic vegetation, that can also be an important other component to mangrove kind of soil carbon stocks. Okay. Now, I mentioned I would talk about Brazil, and I've kind of focused down a little bit on Brazil in this talk. Brazil's got second largest coverage of mangroves, about 1 million hectares, depending on which kind of study you look at, but roughly around kind of 1 million hectares. You got a really kind of varied coastline. You got macrotidal up in the north, mesotidal in the kind of northeast, and then microtidal down there in the south. And from that, you can break it down into a range of different areas. So you've got the AMMC, which is the Amazon macrotidal mangrove coast, and the SAE, which are going to be the two kind of areas that we're focusing on, which is the semi-arid equatorial coastline. Okay, so that's the one that's up there in the north of Brazil, from kind of Parnaíba down to Cabo Branco, and then there's the humid coast that's a little bit further west, which has that very, very large mangrove ecosystem, predominantly around that kind of Bragança area, which you can hopefully see just up in the top between, just directly west of Parnaíba. There's a very, very thick green part. That's one of the largest mangroves in the world. Okay, so you've got two quite different ecosystems. So I'm going to focus down on the differences in carbon sequestration for these two regions in Brazil. And they are quite considerably different between the two in their kind of morphology, and also in their kind of size and structure. Okay, now I'm going to just report some information that from a study that I've undertaken in the northeast of Brazil. Okay, so this is in a semi-arid part of Brazil. So this is in the SAE region, and this is from 3 mangroves in around kind of Fortaleza, which is the capital of the state of Ceará. Okay. Now, Ceará, I've got a picture there just to give you an idea of what we're kind of looking at. So the bulk of Ceará is kind of in that tropical hot semi-arid, but the bulk of the coastline is in that tropical mild hot semi-arid, although you have got patches where you've got tropical hot subhumid. Okay. Now, up here in the northeast of Brazil, we've had over the last kind of 30 years, there's been a slight positive a slight increase in the extent of the mangroves. Predominantly, this is from kind of increases in bar formation up in some of the rivers, particularly where you've had kind of decreases in freshwater inputs due to damming of the rivers. Okay, so that means that you've got suddenly a slight lowering of the water levels, and therefore you get recruitment of mangroves in some of the bars in the rivers, particularly in the upper estuary. There have been some losses in some areas, predominantly due to logging or kind of land conversion. Some of that land conversion is through kind of illegal settlements, and some of it's through kind of legal settlements. Also, as a result of kind of aquaculture conversion, and to a lesser extent, particularly in the kind of the fringing areas of the estuaries, you've had some decrease in the extent of the mangroves in the lower part of the estuary. Okay, so I said I was going to kind of focus down on 3 specific areas. So there's the Rio Ceará, which is over in the west of the city of Fortaleza. Rio Coco, which runs right through the center of Fortaleza, and the bulk of the drainage in the lower part of that estuary is from the city directly into the river. Okay, so a lot of kind of urban input to that mangrove. And then you got Rio Pacochi, which is the one that's over in the east side of the city, that you can see is kind of bounded by dunes on both sides, but and the kind of dune movement is from kind of east to west. So, from a Heliosierra perspective, it's been supplied with less sediment from the offshore zone since the development of the port of Mucaripe, which you can see is that kind of that point that kind of sticks up in the center of the city, and the big groin that was built in the 1950s. However, there's also a greater supply of fluvially and aeolian derived sediment. All of the three rivers that I've just mentioned carry less than 100 milligrams per liter of sediment in the wet season, and this is typically double that of the dry season. So dry season is about 40 milligrams of per liter over the dry season. In the dry season, the majority of the suspended sediment is carried from marine sources. So they're carried up the river with the incoming tide. This is derived from kind of beach sediments. The clay fraction is very, very low in Heliosierra, typically about 2 to 10%, and it's mostly kind of smectite. In Heliosierra, sand is like 85% of the sediment with little variation over time. So we looked at quite kind of cores in that area. And of this, about 60% appears to be derived from marine sources and about 25% from aeolian processes. And the silt and clay are derived from the upper catchment. Okay, now in Rio Coco, the principal source of sediments from the offshore zone is from the offshore zone and also aeolian sources, but the huge amount is from the urban and industrial kind of inputs from the city. Okay, similar proportions in the upper shore, upper kind of mangrove, the higher elevation part of sand to Heliosierra, so roughly about 85% of that is sand. However, there's a much lower proportion that is marine-derived sand. So a larger proportion of that is actually aeolian. Okay, that's 40% to 45%, which is contrasting with the Heliosierra one. Okay, now there's also in some parts you've got high proportions of silt and clay compared to Heliosierra. And it looks like in that area, both the lower shore mangroves and the upper shore mangroves are keeping pace with sea level rise. Okay, so there's quite a contrast between those two areas. You've also got, as you find in most of these mangroves up in the northeast of Brazil, you've got another part of the mangrove which is what we call the apicum, which is these hypersaline salt flats. Okay, so they actually store carbon as well, and they provide a wide range of other ecosystem services. Then moving on to Rio Pacochi, okay, which is this site here. It's very kind of similar type of mangrove to the other two. But the principal source of sediments is from the offshore zone and aeolian deposits. A lot from aeolian deposits. And prior to the 1980s, the predominant sources were from fluvial sources, okay, with much greater proportions of silt and clay. So if you have a look at the bottom of the cores that were taken, there was much more silt and clay to be found there, which obviously is better at kind of conserving organic material. However, there was decrease in discharge in the river due to dam building and the extraction of water. So that means it's lowered the river level in that area, and that means that in actual fact you had that switch from fluvially dominated sources of sediment to kind of aeolian and some marine sands in the lower catchment. Now, I took a lot of cores in those sites, and I kind of did some dating on some of those sites to get an idea of how they, with depth, what were the kind of depth age relationships. Okay, so you can see that the dating in all of these sites doesn't go before kind of 1900. Okay, so you've got about 120 years worth of sediment accretion, between 120 and 110 years of sediment accretion. Okay, so we get an idea then of what the date of each depth of the sediment was. From that, we can calculate once we know how much carbon is actually stored in there, what the carbon accumulation rates are, or carbon sequestration rates. And as you can see, they're fairly high compared to kind of global averages, with in the very top of the heel cockle one, we're at about 10,000 grams per meter squared per year, although it kind of goes down and it's more in the hundreds in some of the lower parts. But you can see that there's quite a substantial difference, with the highest amount of carbon inputs being found in heel cockle, which is the one that's kind of sat in the middle of the city. Okay, so much lower in the two that are either side, although slightly higher in heel Sierra than in heel Bacochi. Okay, so just to kind of put it into a little bit of context, we can kind of have a look at, okay, how much was that as a kind of mean over that whole time period? So heel Pacochi between 890 and kind of 1,553 grams per meter squared per year. Heel Coco, we got there about 3,248 in the lower kind of mangrove, and then down to about 592 in the upper mangrove. And then heel Sierra sitting around that kind of 200 to 220 kind of mark. Now, how does that compare with kind of global estimates? So Alongi did an assessment of mangrove carbon sequestration in 2012. Hopkinson in the same year did a kind of similar one, and kind of got slightly different values based on the data that he was assessing. But you can see there that it's between about 134 grams per meter squared per year to about 226 grams per meter squared per year, which you'll see that kind of fits within that boundary. However, as you can see, particularly for kind of heel cocoa, it's quite substantially higher, and that's most likely due to the fact that there's a huge amount of organic material that's inputted from the city. Okay, so that's exacerbated those rates of carbon sequestration. So really quite high compared to those kind of global averages. And Brazil is one of those areas where there's been very little work done on carbon sequestration, or even in blue carbon in general. In actual fact, in the southern hemisphere, there's been very little study undertaken, apart from in Australia. So the majority of the mangrove studies on blue carbon have been undertaken in the northern hemisphere. So, and as I mentioned in the last lecture, there's quite substantial regional variation between mangroves, and having these kind of global averages that are discounting a large proportion of the mangroves in the world, particularly as Brazil has kind of is in second place from a country perspective. It's really important that these kind of studies are undertaken further. Now, then I said I was going to compare two different sites. So one's that's kind of semi-arid northeast of Brazil, and then we've got this kind of this humid north coast of Brazil, where the bulk of the mangroves in the country actually occur. So up here in the north of Brazil, from just at the bottom of the tip of the north compass in the southern part, you can see there's an inlet there, which is in Maranhão. Directly west of that, there is an enormous mangrove that going all the way along to the Amazon estuary, and this study was undertaken in the Amazon estuary on the island of Marajó. Okay, so Marajó is the largest fluvio-marine island in the world, and I did a study across kind of the all of the coastal kind of area of Marajó, and it's quite different around that island, but it's predominantly kind of mangroves up in the north. Now, comparing north of Brazil to kind of the northeast of Brazil, you can see that it's predominantly around that kind of that humid rainforest, or humid kind of monsoonal type of climate. There has been an increase in the last 30 years in the extent of the mangroves. Typically, those increases have been in kind of former salt marshes or apical areas. So, and the salt marshes are typically on the inland side of the mangroves. Okay. However, there has been a decrease in extent at the seaward margin. So what we found is that the mangroves there are typically moving from the kind of seaward side and kind of migrating inland. Although that does mean that they are kind of increasing in overall extent. Now, from these study sites that I've been working in, you can see there's Chaves and Jaranduba. So those two that are in the north of Brazil, they're fully mangrove. So the only species that you will find in those areas are kind of mangrove, and they're predominantly kind of quite sandy type areas. In Afua, which is up there on the north coast, and Camará and Pesqueira, those three sites there, they are mangrove dominated. So the predominant species that you find there are mangroves, but they do have some Varzea plants in the area. Now, Varzea is an Amazon flood forest type of ecosystem. So there's quite a bit of freshwater input that travels through there, that's traveling out through the Amazon estuary, and this is where the Tocantins and the Amazon kind of join out in that estuarine area. Then down in the south, you've got Ponte Pedras, which is Varzea dominated, although there's still quite a few kind of mangroves in the site. And then right down in the south, Breves and São Sebastião, they're fully kind of mangrove, fully Varzea ecosystem. Okay, so I've done a comparison between the rates of carbon sequestration in the mangroves up in the north, and then down to kind of the Varzea in the south. Now, these mangroves, as I mentioned, they're pretty enormous, and the area is quite difficult to access. Okay, so the mangroves can be extremely extensive, and really the only way to kind of undertake the study was by helicopter. So fortunately, very kindly, the governor of the state actually lent us his helicopter to do the studies in that area. We collected a range of different cores from all of those sites. Okay, so cores collected from the upper and lower mangrove. So that was basically we kind of looked from an elevation perspective, and there's kind of different species that you get in the kind of the lower intertidal and the upper intertidal there. Again, kind of did the same as before, historical sediment accretion rates, calculated using lead-210, using the CRS method and season 137, then some sediment analysis and soil organic matter analysis. So we basically took those cores, cleaned them all up, and then kind of undertook the analysis, same as we did for those sites in the semi-arid northeast of Brazil. Now, as you can see there's quite high levels of organic material. In actual fact, in some of those sites, it's kind of around about kind of 80%. So really kind of high levels of organic material, extremely peaty. However, some of them were a little bit lower and kind of a bit more kind of standard mangrovey, between that kind of 10 and 20% of organic material. So the ones that have the richest organic material were those that were kind of in that Varzea type ecosystem, much more so than in the mangroves. But the mangroves they've got fairly high levels of organic material from a mangrove perspective. Again, did the same thing as before, undertook some dating of the sediment. So we looked at a kind of date with depth. So from about kind of 2020 back down to, I think the oldest ones went back down to about kind of 1850. So you got that 150 years of sediment accretion and organic material accumulation. So we kind of linked that to carbon accumulation over time. So you can see there that there's some very, very high levels of carbon accumulation. Some of them kind of up there in the kind of 8,000, 9,000, 10,000 grams per meter squared per year. Some of them a little bit lower, around that kind of 60 to 180 grams per meter squared per year. So again, I did the same thing as in the previous study. I kind of looked at the means over the whole kind of time period with a bit of variation in there. And you can see that some of those sites are in the kind of 2 to almost kind of 4,000 grams per meter squared per year. Others are much more in that kind of hundreds, 100 to kind of almost kind of 1,000. So still quite high rates of kind of carbon sequestration. But if you have a look at that, you can also see that from a kind of global mangrove average between those two studies that I mentioned previously, pretty much all of those sites have much higher than the global average rates of carbon sequestration, particularly those that are in that kind of Vasia dominated or fully Vasia type ecosystem. Although even those that are in the fully kind of mangrove area would still have pretty high rates of carbon sequestration compared to global averages, which obviously from the perspective of kind of global averages, leaving out sites in South America will have an impact on those global mangrove average calculations. Now, why is carbon sequestration so high on Marajo? Okay, so kind of had a look at this. First off, it's adjacent to the largest contiguous mangrove in the world. Really high productivity, and some of that organic material is actually being exported. And due to the predominant current direction, the movement is from east to west. So some of that is being deposited, is being taken out of the mangrove and kind of deposited in the kind of outer estuary of the Amazon River. Okay. Second point, it's in the estuary of the largest river by discharge volume in the world. So a huge amount of organic material is being dragged down from that extremely large catchment and deposited around in that estuary. And a large proportion of that is being deposited in the estuary where those kind of forests that run down the kind of south and the west of Ilha de Marajó are located. So you've got slowing down of the current, slowing down particularly around those kind of flood forest areas and deposition of the organic material. So large kind of inputs from that. In addition to that, it's also in the estuary of the third largest river by discharge in South America, Tocantins, which also has a very large catchment with high productivity tropical forests in that area. So another source of that organic material being deposited in the site. Now, we've also kind of looked, and about 50 to 95% of the carbon in the mangroves is derived from marine plankton. So I mentioned that in those kind of sources. So some of it's due to productivity, some of it's due to productivity of adjacent mangrove ecosystems, but some of it is due to the rich kind of productivity of the marine ecosystem that's adjacent. Okay, so a large proportion of that carbon actually comes from marine plankton. In addition to that, the mangroves are potentially maintaining about 1/5 of litterfall. So if we looked at litterfall production and when we kind of calculated what the inputs of that would be, so that's a potential other source of the carbon. And then obviously, as I mentioned previously, there's extremely high proportions of carbon that are derived from the upper catchment, particularly in the Vasia and Vasia kind of mixed mangrove that you find in the kind of inner parts of Marajó up the estuary. Okay, now how does that kind of impact on conservation? First off, those extremely high carbon sequestration rates highlight their importance at global scale with potential to support conservation. From a supporting conservation perspective, if we allow those mangroves to be developed on or converted to aquaculture or whatever, then they will suddenly become a carbon source rather than a sink. Okay, so it's important to highlight that when considering conservation. Mangroves in the area in the north of Brazil are kind of well preserved, and same to kind of northeast of Brazil, although urban expansion and overexploitation represent growing threats to their integrity, okay, from a legislation perspective. Sea level rise in some of those areas is threatening the lower mangrove, as we've seen kind of in other parts of the world. And land use pressures in some parts of Brazil are threatening kind of those upper mangroves, the ones that are at the terrestrial edge. Okay. From a Marajó perspective, Várzea forests on the island are severely degraded through the years from intensive agriculture and ranching that is occurring in the kind of adjacent terrestrial lands. And then from an Amazon Várzea perspective, we usually don't talk about this from when we're kind of thinking about blue carbon, but Várzea forests, they act very much like mangroves, and they're the most species-rich floodplain forests in the world, and pretty much poorly understood. There's limited protection to Varzian mangroves in that region, and opening them up to potentially damaging activities, including planned offshore oil and gas exploration, could have that strong kind of impact on their ability to perform those vital ecosystem services. So from a summary perspective of all of those sites, first off, the highest rates of carbon sequestration of any studies that I've found are found in the Amazon macrotidal mangrove coast. High rates are still occurring in the semi-arid equatorial coast, and as we had a look at that, comparing it to kind of global averages, they were quite a bit higher. Okay, rates of carbon sequestration are higher than other global regions, mostly in Brazil. They're not under threat from sea level rise, but that's predominantly due to the fact that they can migrate inland. But where you've got hard infrastructure inland, or due to to geomorphic constraints, such as you find particularly in kind of the southeast of Brazil, they're much more likely to be under threat. And as it usually kind of occurs at the end of these talks, more work needs to be done on conserving the ecosystems from a blue carbon perspective, but things should never be focused on blue carbon, because sometimes people can kind of focus on the carbon aspect and neglect those other ecosystem services, including the important biodiversity and supporting local populations. Okay, so that's kind of my summary of of mangroves and kind of blue carbon, and then I think we're kind of ready to go over to any questions.
Great, thank you, Ray. That was an excellent talk once again. So at this point, open it up to questions. You can put your questions in the chat if you would like, or we also would like you, if you want, to just turn on your excuse me, your camera and your microphone, ask your question live. And I see we do have one question already in the chat from Sediment. How did you measure sediment accretion rate with 210 and cesium 137? And can you, excuse me, suggest a manual for soil data collection?
So I've got extremely detailed explanations on how you can calculate sediment accretion rates using lead-210 and cesium 137 in some of my papers. You could have a look at the one on vertical accretion rates in the semi-arid northeast of Brazil. You can have a look at the paper that I've written on Arctic salt marshes as well. And there's good explanations in there. Andy Plater from Liverpool has written some really good papers on that. And also Andy Cundy from University of Southampton. They both work at the two different national oceanography centres here in the UK. Chris Kraft in the US has written quite a few papers on this as well. So there's some really good kind of papers out there from the UK and US on calculating sediment accretion rates using those. But cesium 137 is pretty simple. You've usually got a single input in the southern hemisphere, and that's from kind of global deposition of radioactive material following the nuclear above test non-proliferation treaty in 1963. As for manuals on soil data collection to estimate accretion rates, they don't do accretion rates in the blue carbon manual. They do kind of stocks. But yeah, any of those kind of papers. There was also really, other than my papers, there's also a really good paper by Green and another one by one of my former PhD students, Mariana Lima. So you could have a look at those papers. Is 210 PB expensive? Yes. It costs I remember chatting to a group of people in the US and I said it's £60 per sample in the UK, which is kind of a good average. And they said, all right, can you do mine? So I'm assuming it's more expensive in the US. There are where I've had it done in Indonesia, that it was through collaboration with a partner there, and where I've had it done in Brazil, it was through collaboration with a partner there, so it didn't come at any cost from that perspective. But it costs a lot in liquid nitrogen, so it can be quite expensive. And unfortunately, I've moved institution. We haven't got a gamma spectrometer anymore.
We have a question from Sean.
Hi, Ray. Thank you for your talk. I enjoyed it very much. It's a follow-up question about accretion rates. I don't know anything about mangrove sediments, but in peat pores, uh, accretion rates decrease with depth because you still get continued decomposition and loss of carbon the deeper you go. So surface accretion rates are always much higher than deeper. Is that a concern in these systems or not, I suppose?
No, in actual fact, if I have a look at my sediment accretion rates, um, they tend to be uh, well, it's irrespective of depth as to whether they're higher or lower. They can be higher at lower depths than they were. It just depends on when you've had kind of influxes of material coming in.
So following from that, so when you see those sharp spikes in carbon over a relatively short period of time, what's the mechanism for that? Is it just like a dumping of organic material, or
It
it
won't be a
doesn't change?
single dumping because it doesn't work at that kind of fine scale. That would be like sub-millimeter, I would imagine. But if you've got a period where you've had, for example, in the upper catchment, like 10 years of like heavy logging and it's producing a lot of kind of organic material that's traveling down, or if you've had a period where you've had kind of sustained storm inputs and it's dropping in a lot of kind of macroalgal material, then that could be that they are usually the causes for spikes. Usually, if I want to know what they are, I look at the historical record, climate record, and you can do kind of stable isotope analysis to get an idea of what the principal sources of the organic material. I've started working with eDNA recently, but and it seems to be quite promising as well, because you can get an idea of a little bit more kind of fine scale sources of the organic material.
All right, thank you.
We have a couple of questions in the chat, but I'm going to take the moderator's prerogative to just follow up briefly with Sean's question. I think maybe Sean is like me. We've done a lot of work where you see diagenetic responses in sediments, and that tends to drive the shape of the profiles, particularly in some of the cores that you showed from the Sierra region. They're fairly recent changes, like in the last 20 years or so. I presume there's enough sort of historical information on changes in the catchment area that you can actually document what has caused those very large increases in the carbon inputs.
Yeah, I mean, well, we've written a paper. It's been in review for the last 19 months and we haven't had the first review back. So but yes, we have looked into that in detail. That's actually Drugio, who has done several of the talks here, and myself, and he actually works in that region. I used to work for the same university as well, so we've got quite a lot of historical data for that region. Yeah.
Okay, we have a question from Alexander. Ray, mangroves can introduce 10% of total carbon introduced into the oceans. Can you give us a magnitude of this input?
For those sites, no, I don't know what the export is, but that certainly for the north of Brazil, there have been two studies that have been undertaken that do talk about that. I would need to reread the paper I wrote to remember what the proportions were from the Bragança mangroves and from the Marajó mangroves. But there have been two studies that have undertaken that for those sites. Alex, if you email me, I'll tell you where they were. I just need to reread the paper. I haven't got it in my head at the moment.
And we have a question from Danielle.
Thank you.
Carbon sequestration assessments are made only through soil assessment. If the total carbon, both above and below ground, were considered, would Brazilian regions rank so high?
That's a good question. I suspect some regions probably would actually, like right up in the north of Brazil, probably growth rates are fairly high and the mangroves are extremely big, like globally enormous. You kind of you look at those and you know that I think I can only think of two other regions in the world that have mangroves so big that have grown fairly quickly, because there's particular conditions in the north of Brazil that mean that they're extremely productive and they can support rapid rates of biomass sequestration, not just soil carbon sequestration. But other parts of Brazil, probably not. In the semi-arid mangroves of Brazil, you've probably seen that the growth rates are fairly slow, and the mangroves are relatively small. So no, I think I talked about that actually in my last lecture. I was talking more about kind of productivity, and then I talked a bit about carbon sequestration in biomass rather than in the soil. This one was more on soil, so I kind of focused down on that.
Maybe I could just follow up on that a little bit. My own background is in doing sediments in lakes and doing lead-210 work in that kind of area, where spatial variability is a bit of a challenge. By comparison, I would think mangroves are many, many times more variable. And given both the expense of doing lead-210 dating and so on, how confident are you in these estimates when you try to start applying them on sort of large areas?
It does depend on the area. Some of them can be extremely heterogeneous in the sediment accretion rates, others less so. And I think probably in the sites that I was in Marajó, they probably don't vary hugely. And in the sites in the northeast of Brazil, they don't vary hugely. But there have been other sites where I've been and I thought, I know this is probably right for this site, this particular place that I've taken the core, but I suspect it varies throughout the estuary. It will vary from the upper to the lower estuary, and it will vary between the lower and the upper mangroves, because you get different rates of or durations and frequency of inundation. So it will vary, but they do give you a pretty good idea. And in some areas, I think they're much more homogeneous.
Okay, thank you. So any other questions for a speaker? Excuse me. Yes, we have one there. What are the other methods to estimate the accretion rate other than using lead-210?
So other methods that I've used have been, particularly if you've got kind of known pollution incidences, you can use things such as various kind of lead isotopes. You can get an idea of the sources of the lead, and if you know what type of pollution incident it was, or other kind of contaminants, you could use something like an RSET, rod surface elevation table. They give you shorter time period rates of carbon sequestration, but you need to leave them in for a little while, and it's not a case of go in and kind of take your calls. You need to put them in and then wait kind of 5 years to get your first bit of data. So it's a slightly different method.
Let me see. I think there's one more question here from Moritz. Very nice talk. If I caught that correctly just now, you mentioned that a very high proportion of the carbon can originate from microbes, plankton, etc. Is that true for the systems you studied only, or is it generally true for most mangroves? Some have quite turbid waters, so I think the relative contribution would be much lower there.
Well, I didn't say about microbes. That is another kind of study, but I did mention about plankton, and that's obviously extremely variable depending on where you're studying. So some areas have extremely high interaction between the marine environment and the mangrove environment. Others much less so. I suspect if we were to look in the northeast of Brazil, the proportions of carbon from plankton would be much lower, but probably a bit higher for kind of for in situ productivity, proportion wise.
Okay, one final chance for questions. If there are no other questions, then I'm going to take this opportunity to once again thank you, Ray, for an excellent talk. You can tell by the number of questions that obviously everyone was highly engaged. I want to just take a moment to alert you to in 2 weeks' time, we will be having the final session of this series when most or all of our speakers are going to come back and join us as a panel. And at that time, there will be an opportunity for people to ask questions. And so I would encourage you to start to think about questions that you might want to ask of any of our speakers. And if any of you are doing work where you have some data that you would like to put together, you could prepare a single slide that you would then be able to share on your screen, get some reaction from our panel, and to get some discussion about any issues or questions that you might have around something that you're doing yourself. If you don't have data, of course, there'll still be plenty of opportunity for asking questions of our panel. And our speaker next week will be Alexander Ferreira, and be speaking on mangrove rehabilitation, restoration methods and strategies, greenhouse gas balance, and global carbon dynamics. So trying to basically sum up some of what we've heard over the series and talk about how to try to keep these systems vital in the future. So with that, once again, thank you, Ray, and thank you all for attending our lecture today. And we will see you next week at the same time.
Excellent. Thank you very much. Enjoy Alex's talk. It'll be amazing.
Yes, indeed.
Excellent, Ray. Thank you.
Yeah, bye-bye.
Bye all.
Bye, guys.
Bye.